We're back, but today's greeting is brought to us by guest DJ Ong.
Yo, what up, nerds?
Thank you, Ong. All right, have a seat, have a seat. Okay, let's go ahead and finish up the notes we started yesterday, which is about logarithmic functions. We ended with trying to figure out what in behavior was just by looking at a function, and we're going to use our knowledge of transformations to pull this off. I did want to remind you before we get back into the notes, the little trick that I was teaching you yesterday was that as long as the base of the logarithm is larger than 1, then these things, their end behavior, their directions they travel can be determined the same way we did for square root functions. So as long as the base is larger than 1, if you have a number on the front that's positive, it reaches up towards positive infinity. If the number in front of x is positive, it reaches to the right for positive infinity. So this graph goes up and to the right from its asymptote. Don't worry about it if you weren't here yesterday. What I wanted to come back to here and remind you, we couldn't use that trick here because the logarithmic base is between 0 and 1, which we found out through a little bit of smarty pantsness, is actually the same as if we had a negative on the front with an exponent, with a log base that was a whole number. So the difference is here the log base had a negative exponent, and that negative exponent, as it turns out, could just be moved to the front of the logarithm as a transformation. Okay. Why, Mr. M? We will remember why because you technically learned about it in Algebra 2. But we'll review why in the next unit when we talk about properties of logarithms and things we can do with them. Okay. Alrighty. I see, again, a log base that is larger than 1, so we know that it should have gone up and to the right, but a little bit of transformations have taken place. This is written in a strange order. Just so you know, I mean, it could stay that way, it doesn't matter, but I'd rather write it in an order that shows me exactly what the transformations were, and that means this positive 2 is actually a vertical shift. I'd like that written at the end. I think it just makes it easier to understand. So this is actually negative log, common log, base 10, x plus 4, and then a plus 2. All right. Because the number in front of x is still positive, this thing does still go to the right. However, because the number on front is negative, it doesn't reach up anymore, it reaches down. So this graph now is down and to the right of its asymptote. What color do I want to use? Blue. More blue? Okay. We know it's down and to the right from its asymptote like this. We need to find its asymptote, and once we know what the asymptote is, then we can write our end behavior. We did this yesterday. So if you weren't here, so sorry. But we have already talked about it before. Remember, the argument of a logarithm must be positive. Just like the base of an exponential must be positive because they're inverse functions. So all we have to do is take the argument of our function and make sure it is positive. This is how we find the domain. And the asymptote is where the domain begins. Subtract 4 from both sides, and we find that x had better be greater than negative 4, telling us that our vertical asymptote is at x equals negative 4. So we're ready to write our end behavior then. Do that in green. Let's write some end behavior in green. The left end behavior approaches the asymptote. It slams into the number negative 4, but it's on the right side of it. So we have that little superscript plus sign. That tells us we're on the right side of negative 4. And at the asymptote, the closer I get to it, the faster my graph is going to skyrocket up to positive infinity. And the right end behavior, well, we've already said it. It goes down and to the right. So as it goes down, it's going to crash down towards negative infinity. It gets there really, really slowly because logarithms are slow. What's that? No, so this is a vertical line. If you shift it up 2, it's still in the same spot. So what you're remembering is the horizontal asymptote of the exponential. For the horizontal asymptote, it is affected by the vertical shift. But for vertical asymptotes, they're affected by horizontal shifts. The other side, like I said, the limit as x goes to the far right. It's going to take a long, long time, but this graph, will eventually crash towards negative infinity. I mean, it's like way out here, but it'll get there. It'll get there. Questions, comments, concerns on that one? Anything I can clear up? Because I know some of you weren't here today due to fast testing. Good call on the reviewing of the asymptote and how the shifts affect it, because I honestly hadn't thought about saying that. We good though? All right. So let's handle the last one of these. Arguably the easiest one on here. Which way does this graph point? Up and to the right. Perfect. And the argument is just x. So what is its vertical asymptote? 0. X equals 0. Make sure we say x equals when we're taking that AP exam. If it's a question where you have to write things, and it's not just multiple choice, you must say x equals. If you just say 0, you're not going to get credit for it, okay? Alrighty, so yeah, points up, points to the right from the asymptote. This is orange, it's not red. And we know, because the argument is just x, that our asymptote is at x equals 0. Oh man, kind of pigeonholed myself on colors here. Left in behavior, heading towards the left, you're going to get stopped by that asymptote at 0. You're on the right side of it though, but at the asymptote, your graph is shooting down. On the right side, the graph is unbounded, so x can grow as large as it wants, and as it does, y will also grow as large as it wants. It's just going to be really, really slow. Logarithms are slow. So what do you think about transformations in behaviors and just generally knowing what the logarithm is going to look like? A couple thumbs up. Nice, nice. Those are silent affirmations, but I'm good with them. Okay. See, he says. What? Nothing? Okay. When what? Oh, bueno. Oh, gotcha. All right. Use the table of values to determine whether the function is increasing or decreasing, and then the concavity. I mean, literally, is it increasing or decreasing? Just look at the y values. It's clearly increasing. They started negative and went to positive, so clearly they are increasing. But the concavity, I mean, do you remember how to figure out the concavity? Whoa, whoa, lots of people talked at once. The average rate of change is going to tell you whether or not it's increasing or decreasing. Okay? So typically we would use second differences, but I think Chris was saying something highly intelligent. What was that? Why can't we use second differences? Because it has to go by 1 on the x-axis. So not that it has to go by 1s on the x, but we need the x's to be a constant rate of change. So yes. So because we have x values not increasing at a constant rate of change, we cannot use second differences. Okay? So what should we do? I mean, honestly, if it was me, I would just start plotting them and you could see the concavity. That's how I would handle that. Then we'll read the rest of the directions, okay? So let's start plotting this, that way we can determine our concavity, because we know that logarithms are either going to be concave up or concave down on their entire domain. So we just need to plot this thing. Let us see. When x is just a hair past 1, my y values are almost to -3. At 2, 0, 6, 1. I mean, it's already obvious what the concavity is. And, well, you can't get 26 or 500 on here, so I think we're kind of stuck here. But it's a logarithm, right? And you can see as you try to travel left on the x-axis, what number did they specifically not go to? 1. They stopped before they got to x equals 1, which means x equals 1 is actually our vertical asymptote, and this thing gets really close to it but does not hit it. Oh, man, go home, logarithm. You are drunk. Let's try that again. Okay, this one's just a fat log. There. Okay. So what is its concavity, up or down? This is definitely concave down. All right, we made a sketch, and it says, can you determine the domain of the function? Well, of course we can. We kind of cheesed it already. What's the domain? Domain. 1 to infinity, yeah. All x values from 1 to infinity, non-inclusive. There. We're going to do the same thing with this next example. I'd like for you to see that the y values are going down. So this is decreasing. And look at these x values. As you try to go, I mean, it looks like we're going unbounded to the right. So what x value did we clearly not go to on the left? -2. So we're probably having a problem at x equals -2. So we've already determined our domain. Now we just need to plot it to see our concavity. I'll do that one in blue. So almost a -2 at comma, a hair past 2. And then at -1, 0. Okay, I think it's pretty obvious what the concavity is. 1, -1. Oh, we can actually get 7, -2 on here. Check that out. And then from there, it just is ridiculous. So clearly, we have a logarithm that looks something like that. What's my concavity? Up, concave up. Thank you for talking to me, lots of people. Appreciate it. Boom. That's not bad, is it? It's really not bad. I'm hoping that you're thinking logarithms are much easier now than they were in Algebra 2. Yeah. See, what I tell you, whoop, whoop, I'm awesome. Okay? What I tell you. Bless you. And not only am I awesome, I'm modest about it. I know. Okay, where's my graphic calculator? It's here somewhere. Here it is. I have to dig in all my pictures that you guys have drawn for me. Boom. All right, check this out. We haven't really seen anything done this way before, but that doesn't mean we don't have these skills. AP is going to focus a lot on, do you have problem-solving strategies, and could you use your knowledge to approach things that maybe look different from what you're used to, right? I mean, hopefully you've kind of gathered that from the test questions that I've been giving you this year, okay? A principal, P, invested at 6.25%, compounded continuously, PERT, and increases to an amount K times the original price after T years. Oh, I forgot the word is compounded. A principal invested at 6.245. Why can't I say this number? 6.25% is compounded continuously. Increases to an amount K times the original price after T years, where T is this. Okay, so here's what we said. We've already shouted out, and I'm fine with that. We saw the word continuously. We know that that means that the amount of money that we have in our account is principal times e to the RT. This is what we know. It says T is this fraction. And this fraction has the letter K in it. K represent how much more times the original amount you have. So if you were trying to get triple your original principal, this would have said ln of 3 over 0.0625. That's what they're getting at. If you want to know how long it would take for you to get 4 times the amount, then it would be ln of 4 divided by 0.625. Okay? That's what that's telling you. So what we're doing here is just identifying values for t by plugging in values of k there. So k is 1, k is 2, all the way up to k is 10. Now we could plug them all individually in, but I'm lazy. So instead I'm going to pretend it says x equals, and I'm going to say the ln of x, not x equals, y equals, man, I am just struggling this morning, divided by 0.06. I can't even type the number 0.0625. Man. And I'm going to go directly to my table because it's going to show me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I can just pull them right off the grid. And I don't have to worry about typing it in over and over and over again. There they are. So when why? This is an awful video. I'm going to lose all my subscribers. Anyway, when k is 1, we get a time of 0 years. The reason why is because if you want to know how long until you have 1 times the amount you started with, well, obviously 1 times the amount you started with is what you started with, so no time has gone by. How long does it take to double? It's going to take, holy crap, 11.09 years to double your money. That's wild. At 6.25% interest. That's crazy. You know why that's so crazy? Right now, the average interest rate in the United States is 0.46%. So this is like, what, 240 times the current average interest rate, something like that? If I can do my basic math, or it's 24 times. It might be 24 times or something like that. The point is, it's a lot more than what we currently are offered. So 11 years. All right. In order to quadruple 22, I'm just going to write, I know I'm supposed to go to 3. Yeah, we'll go to 3 decimals. 22.181 years to multiply by 6 times your amount of money. 28.668. 33.271, and lastly 36.841 years. Right off the table. Boom. It says use a graphing utility to graph this function. This function. What that means is my outputs are t from the table. My inputs are k. It says x, and the reason why it says that is because, your graphing calculator is always going to show you x and y. But our interpretation is that the x's were k values and the y values were time. And it says to graph that. And we're going to use it on the window that they showed us. I mean, I already had it there, right? I'm going to go to my window. I'm going to have my x's, which are my k values, go from 0 to, I'd say, looks like they went to like 22.5. I'm just going to go 0 to 20. And my y minimum, which is time, goes from 0. Let's cap it out at 60. And they went by tens. Actually, you know what? Let's make it real fun. Let's take it up to 22.5 and have the scale go by 5s just like they did. There. And then 0 to 60 and go by tens. Right? Unless that's like 60, like 2-ish. I'm just trying to make it look exactly like this. Is that not what yours looks like? Did you close your parentheses around your x? And your graph doesn't look like mine? Oh, okay. There's no numbers on here. So if we wanted to, we could kind of pin them in according to the table. 1, 0 is like, I don't know, if we had to guess, where is, I have to have 4 marks. One comma 0 would have been here then. And 2, 11.9 is here-ish. 4, 22-ish. 6, almost 30. I think we're getting the idea, right? So it looks something like this. Looks like that. Comfortable? No big deal? Yeah? Okay. Suppose you had $1,000 to invest. Your function for the amount of time that it would take, or actually for any time, I guess, for doubling, tripling, quadrupling, is right here. Use this function to verify your answer from part A. Basically, what was done was you needed to solve for t. So we need to get t alone. We need to get t alone. We comfortable with that? Yes? Awesome. Suppose you had $1,000 to invest. Your function for the amount in the account after any time would be this. Use this function to verify your answer in part A. Alrighty. The real question then is, where's k going to come from? That's the real question. Well, in order to answer that, what we have to remember is what k represents. K represents a multiple of our starting amount, right? I'm going to make this question even better. I'm going to show you that it doesn't matter that you started with $1,000. I say we call the function the amount that you'll have after a certain amount of time is whatever your principal is, e to the r t. And we know, again, that k represents a multiple of our starting amount. That means a of t is any multiple of our starting amount. That's what we were told that k represents. So if k was 2, we would have $2,000, right? 2 times 1,000. So it actually doesn't matter what the principal investment was. That's how exponential things work. We could talk about yearly percent change without ever talking about how much money we actually had in the account, because it doesn't matter. So what I'm going to do is I'm going to replace this with KP. I could have just as easily written 1,000 here and 2,000 here, 3,000, 4,000, 5,000, K1,000. Okay? I could have written any multiple of 1,000 there. So call it 1,000 K or K times 1,000, whatever you want to call it. K times the initial amount. I'll do the rest in blue. I now have K times the principal amount is the principal amount e to the 0.0625 t. Remember what K represents? It's us doubling our principal, tripling our principal, 4 timesing our principal, 8 timesing our principal, whatever. Let's start solving for t. What's the very first thing that I'm going to have to do? Start getting t alone. What's the first thing that has to go? You have to divide both sides by p. And that is why it doesn't matter how much you start with. Because the very first thing you're going to do, someone please get the door. The very first thing that you're going to do is divide both sides by the principal amount, and it will cancel off of both sides. That's why we could make p any number we want. That gives us k equals e to the 0.0625 t. That pesky e, how do I make e go away? Lots of people said it, which is great. I'm going to take the natural log of both sides. So ln of k and ln of this stuff we know on the right side, the ln and the e are inverse functions of one another, giving me the ln of k equals 0.0625t, and obviously divide both sides by this number to finish it out, and we have accomplished the end of the notes. Have I goofed something up? Oh, okay. I heard two people talk at once, so I thought maybe I made a mistake. K times P, not K of P. Mm-hmm. So here's how this works. Imagine I had put a 1,000 here, and you wanted some multiple of 1,000. Then you would say 1,000 times whatever multiple you wanted. So you would have put a 1,000k there. And the very first thing you would have done is divided both sides by p, and you still would have had a k there. So what I was saying was k times p is going to be some multiple of your principal. That is an amount of money that you end up with. Okay? Any other questions on it? And DJ Ung, you can shout it out if you want. They'll hear you. I don't know, tell them thank you or something.
Hey man, thank you so much for watching, man. Subscribe, like, and
comment,
and we out.
Link, merch in the link tree below. Yeah, all that good crap.